Oops, sorry about that. We're going to go over some polar forms for conic sections. And the point of this video or this lesson is to learn about how to represent conic sections in polar forms. And one of the reasons why this is handy is because when you have a polar or the conic section in polar form, it makes computing the area as well as some other things, arc length, a little bit easier. So let's begin by talking about the parabola. The parabola is just the set of points that are in equal distance from a particular point called the focus and a line called the directrix. I'm not going to go into the gory details of how to derive these formulas, but I wanted to at least show you where they come from so that you can look in your book. In fact, you hopefully did look through your book already. At any rate, we're going to put the focus at 0, 0, and the d is going to be the distance to the directrix. Okay. Now, each point on this parabola is going to be written as r theta. And so if q is a point on the directrix that's closest to the point P, then the distance from the point P to the point Q will be the same as the radius, because remember the focus was going to be at 0, 0. So the distance from the point P to the point Q is the directrix, that's the location of the directrix is d, minus the x value for the point P. And the x value for the point P is r cosine theta. At any rate, we want to make sure that this is the same as the radius, or the r value for this point P. And so it turns out that you can take these things, set them equal to one another, and and then rearrange slightly, solve for r, and you get this equation. R is equal to d over 1 minus cosine theta. You can pick any value you want for d. In fact, let's just switch over here to Maple for a minute. And I've written a little procedure for all the conic sections, but for now, let's just go ahead and plot the parabola with a d value of 2, let's say. So I'm going to plot, let's see, remind myself of this. This will be 2 over 1 minus cosine of theta. I'm just going to use t because I don't have to type the word theta in. And t is going to range from 0 to 2 times pi. And I want to be polar. Sorry about that. Oh, and I spelled this wrong. It's coordinates. And I see one other mistake I made. I need to put a t in here. T. Okay, let's see if this works for us. Yeah, there it is. There's our parabola. Let me close in on this or zoom in on it because you can't really tell where the directrix is. So let's go ahead and change the viewing window. This is similar to what you do on your calculator when you change the window. It's similar. So there it is. You can see here that the focus is at 0 at the origin. And the directrix, although it may be hard to tell, but the directrix is 2 units away, so at -2. So that's sort of a general form for a parabola, and it's a parabola that opens out to the right. Now, if you want it to open to the left, that's pretty easy. I'll make this a little bigger for you. There we go. We can make it open to the left by changing this minus to a plus. There it goes. And if you want to go up and down, just change cosine to sine. Oops. You probably found the page in your book that shows the 4 pictures that look similar to the 4 images that I'm putting together right now, that show you which direction each of those conic sections are going to go. Anyway, that's the parabola. And The main thing to note is this formula over here. Now let's talk about the other conic sections. It turns out that each of the other conic sections has a directrix, and the directrix has a slightly different property than it does with the parabola. So here are the definitions for the ellipse. The ellipse is the set of points with the property that the ratio of the distance from each point to a fixed point, that's the focus, and the distance from each point to the fixed line, the directrix, is a constant between 0 and 1. And that constant happens to be equal to the eccentricity. Hyperbola is similar, except for the constant is greater than 1. So the main thing to note here is that instead of, as with the parabola, in the parabola, the distance is constant, so that the distance between the focus at each point is equal to the same as the distance from the directrix in each point. With an ellipse, the distance from the focus to the point is maybe 1/2 the distance of the directrix to the point, and with the hyperbola, it may be twice the distance from the directrix to the point. At any rate, that's really, that just shows you that you can write these as, you can write an equation of a hyperbola or an ellipse using a directrix in terms of, as long as you keep track of this. So here's the polar form for each of these. And E there is the eccentricity. So these are conic sections, and the E is the eccentricity. D is the distance from the origin to the directrix. And then the cosine and the sine act in the same way as I just showed you, that when you have a net minus cosine in the bottom, then the focus that is, I guess the arc that is closest to the origin will be opening to the right. And if it's negative, it'll open to the left. This is found in your book. Let me find the page because it's bothering me. There it is, page 729. You find this same information, sort of pictures here, that if you have a plus, the arc opens to the left. When it's a minus cosine, it opens to the right. And the same thing with the sine and the sine, it'll open up or down. Anyway, let's experiment with this a little bit. I have a little program that I wrote to called my Conic program. And here, the first number is the eccentricity, and the second number is the distance to the directrix. I believe that's the way I wrote it. Yeah. So there's my conic section. Whoops. And so if we change this, if we have 1.7, that's an eccentricity greater than 1, you end up with a hyperbola, as you can see here. Let me change this to 0.7 so you can see the difference. Now I get an ellipse. And each one of these is a cosine. Specifically, I was working with 1 plus e times the cosine in the denominator. So this is the cosine. And if I change this to 1, I get a parabola. Let's see, with a little bit more experimentation, we can change this to a very large eccentricity, something like 0.9. And it's hard to tell that this is an ellipse. So let me just zoom out a bit, or actually, I won't zoom out, I'll just change the distance to the directrix. I think this will do it. There we go, and you can see, change it a little bit more. Makes the ellipse smaller, but the same proportions. And you can see that this ellipse is very eccentric. In fact, I can maybe change this to 0.95, and you'll see a very eccentric ellipse. There. In fact, let's go to Halley's Comet, is a 0.97. So this is an ellipse with an eccentricity of 0.97. We can contrast that with the hyperbolae. So here's a hyperbola. Whoops, let me change the distance to the directrix. There we go. And because of the way that Maple graphs these, you end up with the asymptotes you can see in there. But the curves are what we're interested in. So there's a 1.97. Let's contrast that with a 1.2. and you'll find that this one is shorter and squatter, so that the curves, the arcs go out more, it's a shorter. Whereas if I have a large value for my eccentricity, 10, it's a tall, skinny, I guess, hyperbola. Kepler's laws we'll go over another time. I wanted to make sure that we could do this stuff. So I'll post another video where I work out some of the problems that are similar to your homework, but this at least will get you started on the homework. And these are the formulas that you really want to focus on with the homework. You're looking for you're looking for the equations. And one other thing before I close here is that this 1 here is in the standard form. So if you have an equation that does not have a 1 right here, you're going to have to do a little bit of algebra to turn that into a 1. Let's say that's a 3. I'll show you this with some of the examples on the next video. But if this was a 3 or a 2, you'd have to divide the numerator and denominator by whatever it was, 3 or 2, to get this. So watch the other video and try your homework, and hopefully you can get through it all. And we'll see you on Monday.